Thank you. Good evening, everybody. Welcome here. Welcome to you here in person and also to all the people connected with streaming. I remember that we'll have also a question and answers session at the end of these presentations, so we will be happy to listen to your questions, and I'm sure that we will have many questions and curiosities about the mission that we are going to talk tonight, because the protagonist, as you know, is planet Mars and the mission ExoMars. ExoMars 2020 had to leave at this time in these weeks, but as you know, because of the COVID pandemic, was delayed to 2022. But we are sure that time won't be wasted, but will be invested in improving more and more this mission, because it's really a pivotal mission for space exploration, and in particular for probably the most amazing enterprise that we can think about, and it's the search for life. So we can say that ExoMars is looking for Martians. So we will discover probably in 2 years or more if there life or if there was life on Mars. And tonight we have the pleasure to talk about this mission with some of its protagonists. First of all, here in person with Armando Ciampolini and Walter Cugno. Armando Ciampolini is Chief Operating Officer of Altec, and Walter Cugno is Vice President, Domain Exploration and Science of Thales Alenia Space Italia. And so both were deeply involved with this mission. And we have also in streaming 2 other hosts, and I hope that they are listening to us. First of all, we have Jorge Vago, who is ESA's ExoMars project scientist, and so he's serving as the interface for the scientific communities interested in the ExoMars program. And Paolo Nespoli, hi Paolo, how are you? Astronaut of the European Space Agency, and recommend because he spent more than 300 days in space in the International Space Station. I just would like to emphasize how important is this mission to know, as I said, Mars, and also to know better the past of the Earth. So while looking for life on Mars, in some way, we are also trying to discover better hints of how life blossomed on Earth. Secondly, it's very important to emphasize the role of Italian industry in this mission. We can be proud of the role of the technological know-how as demonstrated by Thales and Altec, and also in the production of the drilling instrument of the rover by Leonardo. And third, I would like to emphasize how this mission is a successful example of space diplomacy, because it's an example of strict collaboration between many different space agencies and many different countries, between the Italian Space Agency, the European Space Agency, the Russian Space Agency Roscosmos, and of course also by NASA, the American Space Agency. And last but not least, I would like to emphasize the great opportunities for youngsters, for young students, because of this mission, because ExoMars has a long past, but it has also a great and outstanding future beyond. So as you know, thousands of people were involved in this mission, but many other thousands will be involved in the future, because space exploration is a sort of long-term mission which involves different generations and is going on and on. And so it's a sort of work in progress, and we have some objectives, but probably the most interesting objectives are still to be discovered. So first of all, I would like to invite Jorge Vago, with the collaboration of Armando Ciampolini, to present and to give us a general idea of this outstanding mission and of its different aspects, both scientific and technological. Thank you very much.
Good afternoon. Can you hear me well?
Yes, we can hear you. Thank you.
Excellent. So, thank you so much for this invitation. I'm very sorry I'm not able to be with you in person. So, I will talk a bit about the search for life on Mars and the ExoMars mission. The first question, perhaps, is why focus ourselves on Mars? And Mars has two important aspects. The first of it is that it's the target that has an interest for life that is closest to us. And the second one is that its past history has been fairly similar to that of our own planet. Now, if we look at the origin of life, which is what this slide is showing, or trying to show, there's two ways to go about it. If you can click again, please. The first one is backwards. And for this, if I can have another click, we can look at, could you click again, please? The machinery of cells, as we do in biology, and try to understand how those came about. Another thing we can explore for, if I can have another click, please, is with chemistry, we can look at molecules and what the precursors of those molecules were. And lately, another click, please, we have as another important tool, genetics, and we can start to look at what we can learn about the genetic programming of life. The other way to go about this, another click please, is to start from the bottom up. And we start from physics, if I can have a click. And important there is, can you click again please? The other way going forward, we start from the origins of the solar system. Click again, please. And we have physics and chemistry. And finally, what we have with another click is in between the two, we have geology. And what you see portrayed here is a hydrothermal system in Antarctica, which is one of the most interesting places regarding the origin of life. So let's dive into the formation of the solar system. Next slide, please. And the first part of the formation of planets regards the coagulation of very minute particles of dust to form aggregates and eventually form small planetesimals. These planetesimals will see each other as they travel through space and have random collisions. And in some cases, they would stick to each other to form larger aggregates. Once an object formed that had sufficient gravity to focus inward the arrival of other objects, it started to grow very rapidly. But as you may imagine, this was a very energetic process. If we could have the next slide. So this was very, very violent, and it gave rise to what we could define today as very large balls of magma. So initially, the planets formed through these violent collisions. Eventually, they would start to cool down, if I can have the next slide, please, by radiating energy to space. So at a certain point during this process, we would have seen something like this. It's a planet that seems to have solidified, where there is still a lot of internal hydrothermal activity and volcanism. And if you could have landed on that planet, next slide please, you would have seen something like this. A hellish environment with lava everywhere and a very, very thick atmosphere where you wouldn't be able to see much. As the planets cooled down, the solidification happened from the inside towards the outside. And very vast quantities of gas came out of this solidifying mantle and crust. And they created the primordial atmospheres, which is what you see on the next slide. What you see here is what is called a supercritical atmosphere, like Venus has today. So imagine a planet that is basically a pressure cooker. The atmosphere is so thick and so dense that it exists in the supercritical state. That is a point at which the atmosphere elements don't know whether to be liquid or gas. They would like to be a gas because they're so hot, but the pressure is so high that it pushes them into behaving like a liquid. Eventually, these supercritical atmospheres would lose heat to space, and when the temperature came below the critical point of water, then the atmosphere was no longer able to hold the water vapor it had, and it rained in sort of a biblical catastrophic deluge. In a matter of a few hours, very large oceans rained from these original atmospheres to cover the entire surface of the planet with global oceans several kilometers deep. And this is something that happened on Earth, on Venus, and probably on Mars. Initially, there was no land on the planets. It was just water everywhere. And if you look at the next slide, eventually what would happen, on the next slide, we would start to get the first emerged lands that were volcanic arcs, islands, a bit like what Hawaii is like today. So if we go to the next slide, I have tried to group all of this in a single slide. And what you see is at the top, the various stages in the formation of the planet we discussed. A bit below, you see what happens on Mars, and below what happens on Earth. On this first slide, we see Earth, and we see that if you go from left to right, you see the first stage during which basically we had a ball of magma. Then you see the raining of the oceans. And at the top, you can see how the first emerged lands appear. That's what is shown in yellow. For reference, you see when the ocean started to cool down below 70 or 80 degrees, that's when the first window of opportunity opened for the possibility of life. Why? Because at temperatures of 70 degrees in the water, you can start to have the first prebiotic reactions where the elements are able to have some degree of stability. And on the right, below at 3.5 billion years of age, you see what is the oldest fossils we have found on Earth of microorganisms where we can be sure those are traces of life. So the bar in blue at the top shows basically when conditions would have been all right for life on Earth. There's another thing that is very important, if I can have a click, and that is, you see here, hydrothermal activity. What does it mean? It means that initially the infant planets were still very, very hot. So there was a lot of heat coming into these oceans and into the land from below. And another thing we have to keep in mind is, if you click again, the meteoritic bombardment. Let us go now to the next slide. Here we see what happened to Mars. And what you see is basically that at roughly 3.8 to 3.9 billion years ago, something very, how should I put it, eventful happened on Mars, and it started to lose very rapidly most of its surface water. And by 3.7 billion years ago, it was basically a frigid, dry desert. So when you talk about life on Mars, you see that the blue bar at the top has become a lot shorter. And to put past missions in perspective, Curiosity landed on Gale Crater, which is 3.6 billion years in age. It's already in the orange part of the diagram. And Perseverance, Mars 2020, is going to go to Jezero Crater, which is roughly 3.8 billion years in age. We on ExoMars are trying to go further back in time. So, next slide, please. Summarizing, when you're trying to look for traces of life on a place like Mars, you have to concern yourself with two things. The first important concept is habitability, and that is the ensemble of conditions that make a place or a planet hospitable to life. In this case, life as we know it. And life as we know it is based on cells, which is the smallest machine capable of life that we all can agree on. The next concept on the next slide that is very, very important is preservation. So if something was alive and died 4 billion years ago, how do the remains of these organisms or collection of organisms make this traveling time from 4 billion years ago to the present day? And these two things are very important. So let's go to the next slide, please. One other thing that we have to discuss today is what we have learned from past missions, and there have been many, but I just want to focus on two. And Phoenix landed in the subpolar northern plains in 2008 and discovered for the first time the presence of a class of oxidants that we call perchlorates, that you see a diagram of on the top of the slide. And these oxidants are key because they are relatively stable, but when you heat them up, the 4 oxygens that you see in red at the edges get released and quickly oxidize any organic molecules, transforming them into carbon dioxide. And what we have done in most of the missions that have gone to Mars so far to search for life is to put bits of Mars ground into ovens and heat them up to look at the organic molecules that would be released. And what we know now, and this has been confirmed by Curiosity, which you see in the lower part of the diagram, is that these perchlorates are everywhere on Mars. And so we have to be very, very careful in how we look for organic molecules, and in particular, when we heat them up. So let's go to the next slide, please. So this was the introduction for the ExoMars mission, and now we'll try to go a lot faster. And as was described in the introduction, ExoMars is a joint venture between ESA, the European Space Agency, with all its member states, and Roscosmos, the Russian Federal Space Agency, but it has also important contributions from NASA, the US Space Agency. Next slide, please. The objective of ExoMars is to search for traces of life, and although we can detect present life, we don't expect it to exist close to the top surface where the mission is going. So we concentrate our search in trying to look for traces of past life. And the way we do this is different from anything that has come before, and we'll discuss this a little bit. Next slide, please. The lander that will touch down on Mars and on which the rover is driving is also instrumented. And this is a responsibility of Roscosmos, and you see here a list of instruments. But today, I want to concentrate on the rover. Next slide, please. So if you think of Mars, you can think of it as a sea of dust. And on this sea of dust, you have the equivalent of icebergs, which are called outcrops, which is what you see on this diagram. If I could have 3 rapid clicks now. So what we're going to see here are the 3 main ways of destroying biosignatures or organic molecules that are close to the surface. You first have UV light, because the atmosphere of Mars is very, very thin. UV light penetrates more or less unimpeded and will destroy or sterilize anything that is lying on the surface. Next category of agents are oxidants, like the perchlorides I described before. And how deep they penetrate into the terrain depends on porosity, on amount of water. And finally, we have ionizing radiation, which is what you see in red, which acts like millions of little knives that over a period of millions of years, acting very, very slowly, will degrade the organic molecules you want to study. So what do we do with ExoMars? We can approach an outcrop and study its mineralogy to make sure it's okay. But then we go and collect the sample at depth. Why? Because we can use all the terrain between the sample and the surface as a shield against radiation. And our studies show that penetration in the order of 1.5 to 2 meters is what you need if you want to recover well-preserved molecules that are 4 billion years in age. Next slide, please. So here you see a presentation of the ExoMars Rover. This is obviously a simulation, and you will see the drill moving from its drilling position to the position that it uses to deliver the sample to this little hand that comes out at the front. And now we're going to go through the various elements of the rover. Could I have the next slide, please? So when you look at the instruments, you have to go from panoramic scale, that is, the rover tries to look what it has around itself, and we're talking about scales in the order of 100 meters to tens of meters, that's panoramic scale, all through to molecular scale. And you do this through a group of nested investigations, where each subsequent investigation is in the field of view of the one before. So let's look at the instruments now. Next slide, please. We start with a set of cameras, and we have a stereo pair where each one of the cameras at the edge, it is not the 2 in the center, but the ones at the very edge of the PanCam, looks more or less with the same field of view as a human eye. Then on the left, you see we have a high-resolution camera that is like a 300 millimeter teleobjective on an SLR camera, and co-aligned with that camera below, we have a Russian infrared spectrometer. And the high-resolution camera and the infrared spectrometer allow us to study far-away targets in order to decide whether we want to get close to them or not. Now, drilling to 2 meters in depth takes us about 5 days. So it's very important that we know what it is we're going to drill into. And for that, we have 2 instruments. A neutron detector, that is also Russian, that tells us how much water there is under us. And a ground-penetrating radar that gives us a stratigraphy with a resolution of 2 centimeters in order to decide how deep we have to drill. And at the bottom on the right, you see the type of information we get from the GPR. Next slide, please. Once we get a sample, we can observe it with this close-up imager. It's like a microscope. But by using a clever set of mirrors, we can also look towards the front, and we can also look with this instrument at the drilling process. Next slide, please. One of the main stars of this mission is the drill. The drill is like a mini oil platform, and we have to assemble 4 elements in order to get down to 2 meters. And integrated in the drill, observing through a sapphire window on the side, we have an infrared spectrometer that allows us to investigate mineralogy while we drill. Next slide, please. As I explained, the sample is deposited in this little hand that comes out at the front, and we can look at it with a high-resolution camera or with CLUPI with the close-up imager. Next, the sample is ingested. If we go to the next slide, if you can click again, please. We see that the sample appearing, the first thing happens to the sample is we crush it. So we produce a powder. And the first instrument to look at it is called micromega. If you click again, please. It's like a camera, but each one of the pixels in the camera is not just red, green, and blue. It's red, green, and blue plus 320 spectral steps in the infrared. So the rover inside has intelligence, if you can click again, please, and is able to analyze the infrared spectral bands of each one of the pixels in order to classify the mineralogy of the elements. And then it uses this, if you can click again, to move the sample under the point-and-shoot instruments, which are the Raman spectrometer and the laser desorption part of MoMA, which is the largest instrument devoted to the study of organics. And if you can click again, we also have a carousel with 29 little ovens, so we can do the studies as they were done on the other missions. The thing that is new about this mission is the ability to extract organic molecules using laser light. This is new, and it's something that allows you to render volatile organic molecules without exciting the perchlorides. So let's go to the next slide, please. If you want to know about more about the payload and the mission, you can go to this issue of Astrobiology. It's all explained there. Next slide, please. So let us look again now a bit at how this mission was put together. Here you see what we call the glove box that was used to assemble the analytical laboratory in ultra-clean conditions in Thales Alenia Space in Torino. Next slide, please. And this is the heart, is the ultra-clean zone part of the analytical laboratory seen inside the glove box train. This was the last picture that was taken before sealing it up for flight. And I have to say, Alenia has done an amazing job. They have been so flexible and have been able to comply with the requirements in such a great way when it comes to organic cleanliness. Next slide, please. So here you see the analytical laboratory drawer already assembled with all the 3 instruments inside before going to the UK for assembly. Next slide, please. This is a video showing the real integration of the analytical laboratory drawer in the rover bathtub, which is what we call the body of the rover. Next slide, please. And here you will see the drill being exercised at accelerated speed. The drill moves very, very slowly, so usually we take accelerated films. Next slide, please. Here you see on the right the rover in Airbus. We needed to calibrate the ground-penetrating radar, so we elevated the rover over a metal plate for this exercise. And in the left, you see it doing some of the tests. Next slide, please. The landing site. Next slide, please. Oxyaplanum is very old. You see here I tried to put in the same graph that we had seen before, that the age of the clays that are the main target we're going to try to investigate, they are dated between 4 and 4.1 billion years in age. So we're going the furthest back in time that any mission will have gone in Mars. And the other hypothesis is that we have targeted a place that we think may have been an ancient ocean. Next slide, please. Very rapidly, some images of the actual hardware. Next slide. So the launch window will open on in September next year, the 21st, and will close on the 2nd of October, and the landing will be in 2022, and the landing will be on the 10th of June, 2023. Next slide, please. These are some images of the carrier module that will take the capsule to Mars and of the qualification model of the capsule in Russia. Next slide, please. Here you see a partial assembly of the landing platform with the ramps extended. Next slide. This is in Torino, in Alenia, and you see the lander with the legs folded. Next slide, please. This is a little bit before shipping the composite to Cannes last year. And next we're going to see some videos of some tests. Next slide. Next slide, we see this is in Lavochkin. Next slide, please. And to conclude, next slide. This was the last picture at Thales Alenia before the composite was shipped to Cannes last year for tests. This will happen again in October soon, but I thought it's a very nice image to end with, and to thank very much everybody who has worked on the mission and is still working on. We hope it will be a great success. And thank you so much for your attention.
Thank you very much, Jorge Vago. Your presentation was extraordinary, and the images were really outstanding. It was like a docu-film. So I would like now to ask Walter Cugno to talk about since we had this general overview of the mission, we can, I think, focus more about the technological aspects and about the work in progress. going on. Please. Più vicino, forse.
We have to consider by looking at
Scusa, forse closer to the microphone.
One thing we have to consider while looking to the wonderful presentation done by Jorge is that we are talking about hardware which have to work millions of kilometers from Earth with even not a real-time communication that Armando will explain better when we'll talk about the rock. And everything should work perfectly after having succeeded in a launch environment, the cruise from Earth to Mars, which would take 9 months, where we have to get there with a working system. And then we have the famous 6-7 minutes of fear when everything will be released and we have to enter and bring our rover and the landing platform on the surface of Mars safely, which is not always the case because in the past many missions has failed. As you know, there has been almost 50% of the mission done to Mars which failed when landing into Mars. That's why we had the first mission in 2016, where we, as Jorge said, ExoMars is made by 2 missions. One was done in 2016, where we have brought our orbiter, which is perfectly working around, doing shines around Mars, which is the TGO, and will act as a data relay satellite when we have the rover on the Mars surface. And as part of that mission, we have the demonstrator, a technological demonstrator, which was the Schiaparelli probe, which has been the key for us as Europe, which we have never been in through mission like this, to collect a lot of data for the landing on Mars, for the entering and descending landing on Mars, which is helping us to have a very robust mission now for the rover mission, to bring the rover finally to the surface of Mars. Then when you are there, you have to be able to get the rover out from the landing platform and get the rover working in an autonomous way. So all the movie and the picture we have seen of the drill, which by the way is an Italian technology developed by Leonardo, which is our shareholder, by the way. It's one of our 2 shareholders. All these operations are done in an autonomous way by the rover, and as well as all the sample treatment inside the laboratory that you have seen in the picture, and all the analysis, collection of data, and sending back the data to Earth, where all the scientific team will have the possibility to assess and to analyze. Having said that, everything should work properly, and there is no way to do any repair, any maintenance if something happens, and that is the key. Is the key why we have not, due to the COVID, mainly to the COVID, we have not completed the project and done the mission this year, like many others has done, and we will do that until 2022. The rover now, the rover is in Torino, the Shell module is in Torino, the full spectrum is in Torino. We are preparing again everything to be moved to our facility in Cannes, where we have all the capability to do environmental testing, which have been already done to prepare for the launch in 2020. However, we will take the opportunity of this further delay to make to a more robust system. We will repeat, we will go through a number of tests. More we do tests, more opportunity and possibility to find a defect, of course, we have, and that will make our mission more robust and the success probability much higher than we had so far. That is where we are, and having said that, is also I want to mention that since we are in Trieste, we are in Italy, that Italy is the leader of this mission for the European Space Agency. European Space Agency is the first contributor through our institution to our national space agency to the mission, and our industry, Thales Alenia Space, with our site in Torino, is the leader for the European contribution to the program, and is managing, coordinating all the industrial team in Europe, as well as our partner in Russia. And many of the technology which are required to do the mission, like the drill, but also the radar, which is one of the key elements of the Shend process, is as well the parachute and many other components and equipment are developed in Italy by Italian industry, and most of them by Thales Alenia Space. So we are, to answer to your question, we are taking advantage of the additional 2 years to go through a repetition and more testing of the system in order to improve the probability of success of, which is a must for Europe.
Thank you, Walter Cugno. And so I'm happy now to ask Armando Ciampolini to talk, I think, first of all, about the rover, which is one of the, I would say, the core of this mission. And we are proud to say that in Torino there will be the ROC, the Rover Operation Control Center, and so it will be driven in some way in Torino. So it's a hard task. Please.
Yes, of course. Altec is a company of Thales Alenia Space and the Italian Space Agency, and we are proud to say that we have already created the Rover Operation Control Center that was ready to operate, and we used it to perform several tests in order to verify the functionality of the connections and the way of processing data coming from the rover, to explore the planet extremely far from us, Mars, at a distance that is varying. There is a time lag that is directly varying from 6 to over 20 minutes, but actually the communication is more complicated. Imagine that the rover is communicating through the orbital system that has been put in orbit around Mars, the so-called TGO, Trace Gas Orbit, with the mission 2016, and from the TGO to the Deep Space Network of ESA, 3 big antennas at 3 corners of the world. From that to Darmstadt, the ESOC Center in Germany, and then finally to Torino, where everybody dealing with the mission is converging. That means all the engineers, all the scientists are there, including, of course, those who designed the machine. Robotic exploration means that there is nobody there who can help you. There is no astronaut. And Paolo Nespoli will explain us what is the difference of robotic exploration with human exploration. There is no possibility to ask somebody to have a look at it if a failure occurs. You have to understand where you are and to understand what's going on in terms of scientific exploration and also working of the machines. So we organize our center with all different features. We have different rooms for different specialities. There are those dealing with to understand where we are, because also the location of the rover is very important. People working on the vehicle itself to understand if the vehicle is working. Then all the scientists, the rover is a traveling laboratory with 9 experiments on board. Jorge explained very well how there are experiments looking around the rover, and those who are dealing with the analysis to be made on the sample taken by the driller. And finally, there is a main control room where all decisions are taken and translated in terms of next steps of the mission. So the mission has the goal to move the rover over 70 meters per day. That looks very little, but is a big step for something that is millions of kilometers far from Earth, 150 millions order of magnitude. So that's the big difference. And with a phasing of activities more linked to the Martian day, the Sol, that is 40 minutes longer than Earth day, than the Earth day itself. So with a continuous shifting, it's like changing the hour every day, roughly. So what we are going to do, we are supporting the team for this additional effort for the risk mitigation.
Thank you, Armando Ciampolini. And so I hope now to see Paolo Nespoli, if it's connected with us. Oh, hi Paolo, how are you?
Ci sono.
Ci sei, bene. Thank you very much. So you are, as we all know, Paolo is an icon of Italy in space. And so we are very proud to have him here now today. And well, Paolo, we are talking a lot about robots in space, and of course robots are implementing outstanding missions throughout the solar system. But at the same time, our hearts are beating really very fast when we see people, men and women in space. So while we are talking about rovers and robots on the surface of Mars, we are really hoping to see in the next few years, or at least in the next few, I would say in the next decade, a man or a woman or a human crew on Mars, and to see and to live the same emotions that we lived when we saw Neil Armstrong on the moon. So what do you think? This time is coming soon, and we are going to see soon a man or a woman on Mars. What do you think?
Well, Gabriele, it's very interesting. First of all, I would like to thank all the people that have organized this ESOF conference for inviting me. I feel I am a little bit an intruder here because we are talking about machines. And, you know, as Armando said, we don't have astronauts, and somehow I almost said, thank God, because they can do something crazy and things like this. So it's interesting that when I was a little kid, I saw the astronaut going to the moon. We were in the late 60s, early 70s, and at that time, everybody was saying, in 15 years, we will go to Mars. And then 15 years passed, and still we were not going anywhere. And then, you know, I was growing, I became an engineer. Eventually, I started working for the European Space Agency, and I could hear, in 15 years, we will go to Mars. And then I became an astronaut, and now I'm retired, and we are still saying, in 15 years, we will go to Mars. Why? Because we are not starting, at least with missions that have a human content. You know, I'm really glad, really impressed by what I saw. The presentation of Jorge is extremely interesting, and it shows us a machine, a system, much more complex than what I thought. I saw this laboratory, this collection of material on the ground, there's an analysis. These really, really complex tasks that have to be done in a location using somehow automated processes that though can be somehow controlled and commanded from the ground. And the ground is not exactly around the corner. It's a little bit farther. It takes like, 15, 20, 30 minutes before a command gets there, comes back. So I understand, after having lived for almost a year on the International Space Station that is very close to Earth, and if I pick the mic and call Houston, they normally reply in a fraction of a second. And I can only imagine what would happen if I would pick the mic, say something, and have to wait for half an hour before I get anything. It's really complicated. It's an interesting situation. It's amazing if I look at what we've been able to achieve these days in terms of technical content, construction, engineering, and everything that we need to do in order to design, build these machines, which, by the way, if you think a little bit, they're starting more and more to look like humans, able to do autonomously certain tasks from the beginning to the end. So we don't need to tell them, move that pieces in one way, then the other, turn it 30 degrees, go down, go up. We just tell them, take a sample from the ground. And the machine knows how to do that. Those are interesting, very interesting things. We see the transformation of robots, of machines, into humans. And strangely enough, if you look at Earth, you see humans becoming more and more robots, meaning that, oh, okay, the shoulder is broken or something, we change it. The knee is broken, the heart, and we keep going. So there is this crossover of capabilities, robot to humans, human into robots. And frankly, I don't see any contradiction. I mean, people always ask me, the robots to Mars, and I understand, but today we as humans, we cannot go to Mars. There are still so many things that we need to understand, so many questions that we need to answer, that we are still back where we were 15 years before we can go to Mars. 15 years from when we will start the program that is technically sound and has enough resources and capabilities, and I would even say autonomy, to really have a technical goal and achieve it without being distorted continuously by other forces, any force that today are impinging in our space programs or in our big programs. So I'm impressed by the fact that we are slowly but surely progressing and getting close to understand if on Mars there was life, how long ago it was there, if there was something else. Understanding a little bit more, because frankly, at least for me, I'm an engineer, I'm not a scientist, an astronomer or astrophysicist. Mars is still a big question. It's still, I don't think we know enough to really say, was it like Earth? We saw on Jorge a diagram before the formation of a planet, and the bluish age, and then the red age. Is the Earth going the same way, and eventually will go the same way? Can we, as humans, understand this process and make sure that we give the correct inputs to make it go the way we want? These are all very, very interesting questions. And yes, I would like to conclude saying that Mars, it's a big step. What we are doing today, what you are doing today, by designing this kind of mission and and make it happen, which is a great challenge. I mean, people do not understand how difficult it is to go to space. They think that sending a robot is easy and whatever. It's not easy at all. And these machines get more and more complicated. I noted down when Armando mentioned the speed of the rover, 70 meters per day, which seems, oh, come on, 70 meters per day. It's a lot. It's a lot of road to cover in this remote situation. And yes, it's a small step. When we will finally be able to send humans on Mars, probably in a couple of days, or in a few days, they will do more than what all the robots that have been on Mars have been doing. They can intervene, they can move. But it's a long, long step. Today, it's still 15 years away. And if we would not have these missions here, if we do not use them to understand more, both on the situation on Mars and how to control and manage these missions, we will not be able to do this step. So I'm looking forward to seeing the rocket take off. I'm looking forward to see ExoMars landing on Mars. I'm looking forward to see the rover going, and I'm looking forward to see the drill go down and perform its task. And obviously, as an Italian, I'm really proud to know that the Italian industry has contributed heavily to the mission. The Italian Space Agency, the European Space Agency, I would say we should do more. We should work together and do more because, Mars is far away. But if you really look at the universe, it's really here around the corner. We need to get to this corner before keep going and going and going. And there's a lot of things that we need to do.
Thank you, Paolo. Thank you very much. We have time for questions, and so I invite you to ask questions if you want, and also to the people connected with the streaming. So I'm waiting for questions. And well, I would like to ask one more question to Paolo, if he's still connected.
I am, Gabriele,
okay,
go ahead.
Thank you. So, of course, you explained to us how hard is this challenge to send humans on Mars. So we'll have to wait for a few more years. But do you think that we'll have to imagine a different kind of astronaut? I mean, we were used to see astronauts during the Apollo missions. Then we saw the astronauts of your generation on the International Space Station. And so what kind of people will be the astronauts which will be sent to Mars? Will be very, very different from you as astronaut and different from your training, or in some way they will be similar to you and to your experience?
Well, Gabriele, I think there is a difference, or at least I feel there is a clear difference between the first astronaut that flew in space and the, let's say, current astronaut. By the way, it's kind of interesting because every year we have a worldwide reunion of all the astronauts, and it's interesting how we look at the Apollo astronaut, or even the earlier one, we look at them like God, and they look at us like, oh my God, you've been in space 1 year or 2 years. For them, it's shocking, totally shocking. Some people have been in space for just a few days. And so it's kind of interesting how today on the International Space Station, the astronaut is really the manpower available, or the human power available in space. And that person needs to be able, essentially, to do everything. So while the regular people think that astronauts are these great scientists or whatever, in fact, I believe today we are people that are able to do anything that can be asked to them, which means, yes, you do science. It's not that you do science, you perform science on the instructions of the scientist, which is, I think, is different. But you're able to perform even complex science because you get trained. But also, you are there to maintain the station, to fix the station if it breaks, or to clean, to unload a supply vessel, or to perform a spacewalk if necessary. So the astronaut is this person that works at 360 degrees, tackling anything that is needed up there. I think this is the type of astronaut that probably would be needed when you go to Mars, because you are in a remote situation. You need not only somebody that is able to execute a detailed timeline, you also need somebody that is able to take actions and understand what's going on and make sure that it's able to handle the system. We need to consider that one of the things that we will need to do in order to go to Mars is to build rockets and environments that are much, much more intelligent than what we have today. I am on the space station, something happened, a sensor sends a command or a message down to the ground, Houston, look at it, and sends up a command. That is easy. That can be done on the space station, but not on Mars, because by the time the message goes down to Earth and comes back, you are already gone if there is an emergency. So we need to have complete different systems that we need to do, and astronauts need to be, I would say, a little bit similar, but a little bit more than what they are now today on the space station. The last thing that I would like to add, which to me it's really interesting, I would think we need to pay a little bit more attention to the psychological part. Because when I'm in space, people think I'm really far away, and it's only 400 kilometers. If I look down at the window, I see the Earth. If I would jump on my spacecraft and come down to Earth, in a few hours I'm back to Earth. But think about you are on Mars, or around Mars. You look around and you cannot distinguish Earth from any other star, and which means you are lost. It's like, being at sea, and one thing is being at sea that you can see the coast, and another thing is being at sea and you don't see anything around you. Where is ground? Where do I need to go? That requires an incredible firmness, an incredible preparation from a psychological point of view, because really you are isolated and confined, and there is not much that you can do if you absolutely need something. So there's going to be this transformation, a little bit more, the last thing, and a little bit more that we need to think is that maybe we need to have astronauts that will pick up again a little bit more this willingness of jumping into something, or something that we don't completely know. I would say that today when you fly on a space shuttle, when you fly on a space station, you are trained so much that there is very little or absolutely nothing that happens in space that you haven't been trained for. But this would probably not be the case when you are on Mars, and so you need to accept it. There was even the situation some time ago we were talking about one-way mission to Mars. Are we ready to do one-way mission? Today I think this is kind of shocking, but if you think about the universe, eventually we will have to do one-way mission. Eventually there will be humans that will be born outside Earth. That's a very interesting and challenging situation.
Thank you, Paolo. It's very interesting that while we have to improve robots, we have also to try to improve humans. And so I'm wondering if Jorge Vago is still connected with us.
Yes, I'm
Yes?
still here.
Oh. Hi, Jorge.
Hi.
Oh, yeah, we have a question for you. Since the next mission will leave, as you said, on 2022, and probably it will arrive in 2023, do we have any idea about the timetable, the schedule of this mission? When can we expect the first results of the drilling and the experiments, and when it's plausible to think that we'll have the first information about the possible traces of life on Mars?
Okay. I think you're going to see first images very, very soon after landing. We expect it will take in the order of a week to 10 days to get the rover off the landing platform. And the reason is this is a very dangerous, from an engineering point of view, maneuver. So we have to make sure that we exit the lander in the right direction, the direction that is safest. Once we get on the ground, we will spend the first couple of weeks investigating the lander to understand how well the engineering of the lander worked. So did the legs buckle? Did we make a big hole in the ground with the descent engines? These sort of things. Eventually, we will set off and start our science mission. Initially, we need to learn how to use the system. So you cannot expect that we're going to drill to 2 meters in the first month. The first hole will probably only be 10 centimeters deep. And as we get bolder and bolder and we understand the system better and better, then we will start to do things that are more daring. When it comes to trying to say something intelligent about the possibility of having been life on Mars, I think it's going to take more than a year. And the reason is that the scientific community is very skeptical. And so to try to convince them, we will need to probably analyze many samples and be sure that we perform different tests with different instruments, and the results of which can only be explained by life. So you will have to be a bit patient when it comes to this big important question. Data will be flowing fairly soon, but the interpretation of the results, and in particular any big pronouncements, that will take time.
Thank you. So you will be bolder and bolder, but also we have to be patient. And so, Walter Cunha, what do you think about the real challenges that we have in these 2 years? I mean, I'm wondering now the lander and the rover are like packed in somewhere, or they are still, as we saw in the images of Jorge Vago, available to tests and controls?
No, they are not. They were packed together. Now they are not anymore. And we have 2 rovers, by the way, in Torino. One which is the flight rover, and the other one, which is one-to-one, the flight rover, will be in Altec to support the operation, troubleshooting, whatever is needed to have a successful operation on Mars, and to simulate on ground what is happening on Mars. We have to be, the patient is one of the things that is characterizing the space project, because if you are, you want to be too quick and to get immediate result also from the technological standpoint, the risk of failure is very high, and we cannot allow the risk of failing a mission like this. It's very complex. You have seen the picture. So, and there is another thing that I would like to mention that Jorge didn't mention, but to find the sign of life on Mars, we need not to bring life from Earth to Mars. And that is one of the things we had to implement for the first time in Europe in order to understand all these how to treat of the contamination aspect and the cleanness aspect on ground in order to avoid to bring bacteria or any sign of life from Earth to Mars. And so the fact that in Torino we have that beautiful facility which allows us to sterilize each and every part which is going to Mars, to test that and check sampling continuously that you don't have any contamination, and also to be able to integrate and assembly things like the laboratory, which is composed of thousands of parts, very smaller, with the glow box, and avoiding any kind of contamination. This is another thing that make the mission on ground very complex, and it's taking a lot of time and a lot of money in order, you can imagine, to be able to do that. That will be repeated when we have the next mission to Mars, which is Mars Sample Return, where at the end of the day, having in mind that this mission will be successful, we'll be at that point bringing sample from Mars back to Earth. But this will be another story.
The next challenge.
It's another story.
Yeah. Anyway, we are sure that we didn't bring any microbe from Earth to Mars during all these missions, because who knows?
I mean, we learned from the
danger of
Americans how to avoid that,
exists.
so we assume that they have done properly before.
So, Armando Ciampolini, I think that it's the curiosity of many people is about, I mean, a day in your operational center, how you physically drive the rover. I mean, from morning to, from the dawn to sunset, how a day in your center works.
The day will be very intense, of course, because imagine that everything is running right. There is a rover. The rover has around a group of stones that can block its movement. There are no roads. So every time you have to build up a 3D modeling of the area around. So the same pictures that are used and the same information that are used also to be for scientific processing are in fact used to understand where the rover is and how to figure out which is the good path to avoid this kind of obstacle and avoid that in a stupid way very expensive and crucial mission can be stopped by an obstacle. And also to understand, in fact, where to go, because there is a sort of strategic planning that is saying if in a month I have to go from one place to the other, but this has to be split in pieces and arrive to 2 days tactical planning, where you have to go 140 meters far from where you are at the moment. And so there is the 3D modeling. There is a possibility to test in our center in advance any movement by means, and any operation by means of the exact copy, the twin of what has been sent on Mars surface. And every team is working following its guidelines. So there is on one day, the engineers, in the same day, the engineers are evaluating that all of the systems are working properly. Each experimenter is taking it's evaluating data from the previous sending of the data. and for its own experiment. And in the end, everything is collected in terms of a unique decision, what to do, and translated in terms of macro instruction to be sent. And the day has to take account of the fact that the windows of transmission and connection with the rover is strictly identified and is varying. It's not always the same. It's the distance of Mars is very large. As I said, you go from 6 minutes to over 20 minutes by direct line, but in reality, this is made longer by the chain of transmission. But as a term of comparison, Moon is 1 second away. So and as Paolo said, the distance of the space station, that is, I mean, the space station is a remote post, but it's 400 kilometers, is less than the kilometers we cover today from Torino to Trieste. So it's, Mars is really far away. And this time lag and this communication difficulty is a key factor. It's also a key factor for, as Paolo said, a human crew there would be extremely isolated and would be extremely difficult to support them. And when we see the window every 2 years, means that every 2 years you have a reasonably good condition to send something there. If you send something to Mars outside that windows, what you could send has to be transformed in propellant and different time to reach Mars. That in that window means 9 months of traveling. So that's why everything has to be made extremely careful. Everything has to be simulated on ground. And that's exactly the job of the rover operating control center.
Okay. So unfortunately, we are running out of time, so I thank you all, and let me thank Armando Ciampolini, Walter Cugno, Jorge Vago, and Paolo Nespoli. Thank you really to all of you for your extraordinary explanations of this mission, which, I mean, it's just beginning, and so we will have a real extraordinary future beyond us. So thank you very much. Thank you.
Thank you.
Thank you.